As you saw on the previous clip, we define or we measure angles in radians, and we measured the distance that the speed with which the ball was traveling in radians per second. A radian is an angle that's about this big, and we define it in the way that I'm going to describe here. Okay, a radian is defined by analogy with an equilateral triangle. An equilateral triangle has 3 equal sides, which makes it symmetric, which means that all 3 angles have to be the same. Since the 3 angles add up to 180 degrees, each one is 60 degrees. And degrees are our usual and our customary unit of measurement for angles. So here's an equilateral triangle. Now we're going to describe a so-called equilateral sector. Now I put equilateral in quotes here because we really, lateral refers to sides, and we don't have 3 sides. In a sector we have 2 sides and an arc. A sector comes out from the center of the circle along radial lines, straight lines coming out from the center, until it hits the circle, and then it intercepts an arc of the circle. Now the equilateral sector is going to be defined for a circle of radius r by the fact that the arc length of this sector is r. The arc length is equal to the radius, in other words. That's why I say this is sort of equilateral, although this isn't a side, so lateral doesn't really apply. Nevertheless, we'll abuse language a little bit and say that a radian is defined by an equilateral sector, a sector whose arc is the same as the radius. Now, an equilateral triangle has an angle of 60 degrees here. If we bend this line out into an arc, since the shortest distance between 2 points is a straight line, this point and this point are going to come closer together because they're being connected by an arc of length r rather than a straight line of length r. And you might want to think through exactly how that makes this angle shrink down to less than 60 degrees. But it turns out that that's going to pull the angle in about 3 degrees to something pretty close to 57 degrees. So 1 radian is less than 60 degrees, a little bit less, about 5% less than 60 degrees. We could ask the question, how many 1 radian angles can we fit around a circle? That's the same as asking how many arcs of length r will fit around the circle, since each 1 radian angle intercepts an arc of length r. The total distance around the circle, the circumference, is 2 pi r. The circumference of the circle is 2 pi r, 6.28 r. Remember that pi is the ratio of the circumference to the diameter of a circle, or the circumference to twice the radius. So the circumference is 2 pi r, about 6.28 r. That means that we can fit 6.28 r's around the circle, approximately. Exactly 2 pi r's will fit around the circle. That means that we're going to be able to fit 2 pi 1 radian angles around the circle, approximately 6.28, but exactly 2 pi r's are going to fit around the circle. The angle from here around to here then is going to be 2 pi radians, and this is how we determine that. This is how we measure that. Now we can ask what good radians are. Okay, what is a radian good for? Well, a radian is really good for comparing arc length to angle. We know that when the angle is 1 radian, the arc length is 1 times the radius. So that if we want to solve a problem like the present, okay, here we see, we're going to say we have a circle of radius 50 and an arc of length 90. The question is, what's the angle here? How many radians in this angle? Now, if the delta s, now let's explain this, delta s is going to be what we call the arc length. Okay? We have an arc length, and we're going to designate that by delta s, the change in arc position between here and here, or the change in distance between here and here. The distance you'd have to move to go from one point to another. If delta s is 90 and the arc is 50, then what can we say about the angle, theta? Okay, again, if delta s was 50, then you'd have an equilateral sector and you'd have 1 radian. But delta S is more than 50, so clearly the angle is greater than 1 radian. Now, if delta S was even greater, let's say delta S was 100. Okay, if delta S is 100, then you have a 2 radian angle because 50 gives you 1 radian, another 50 gives you another. But of course, delta S in this case is only 90. Now we've bracketed the angle. Since delta S is between 50 and 100, the angle's between 1 and 2 radians, and we can see it's a lot closer to 2 radians. Well, this probably suggests using some sort of proportionality. It certainly does suggest it. It might suggest it to you. If delta S is 90, then theta is 90 over 50 radians, or 1.8 radians. That is, for every 50, we get a radian. So if we take the ratio of the arc distance delta S to the radius 50, we get the number of radians. And of course that would work. If we had a delta S equal 50, we'd have 50 over 50, which would be 1 radian. 100 over 50 would give us 2 radians. Let's generalize what we just did. Okay, if we have a delta S and an R, how do we find the delta theta, the change in the angular position from this line to this line? Well, what we just did before was we divided the 90, which was our delta S, by the 50, which was our R, and we got 1.8, which was our delta theta. So when we divide delta S by R, we get delta theta. We say then that delta theta is delta S over R. And these examples help you understand that, hopefully. We can of course solve this for delta S and see that delta S is R delta theta. These are important relationships and you should understand them, you should know where they come from, and you should certainly be able to use these relationships anytime the situation calls for it. One point in using radians then is that it's much easier with radians than with degrees to relate theta and delta S, if you know the radius of the circle. If you had to do this calculation in degrees, you'd have to use a proportionality. Delta S over the circumference equals your angle over 360 degrees. That's not really hard to do, but it's more trouble than you get into if you use radians. Another good reason for using radians is that when we do calculus, the calculations that we do with trigonometric functions, the calculus operations that we do on trigonometric functions, are immensely easier if we use radians for our angles. So radians are very important units. We need to understand them and we need to use them where appropriate, and in most mathematical applications, radians are the most appropriate.